Good morning, everyone. Today we'll be discussing one of the most important CPU scheduling algorithms, which is priority scheduling. This concept ensures that the most important tasks in a system are executed first. Imagine you are managing multiple tasks like listening to music, downloading a file, and attending a Zoom call. The operating system uses priority scheduling to decide which task gets the CPU first. Most likely the Zoom call, since it's time sensitive. By understanding this algorithm, we'll see how modern systems balance efficiency, speed, and responsiveness. Now let's begin with the basics. In priority scheduling, every process in the ready queue is given a priority number. The CPU will always execute the process with the highest priority. The main rule is simple. The CPU should never sit idle if a higher priority task is waiting. For example, in a hospital management system, if a background report is running but an emergency alert appears, the CPU has to switch to that alert because it has higher priority. Priority scheduling can be implemented in two main ways, which is preemptive and non preemptive. In non preemptive scheduling, once a process starts, it keeps running until it finishes, which is without any interruptions. It's like giving someone a microphone and letting them finish speaking before the next person begins. This reduces context switching overhead. Whereas in preemptive scheduling, if a higher priority process arrives, it can interrupt the currently running process. It's like a doctor leaving a routine checkup to handle an emergency patient immediately. Preemptive scheduling is crucial for real time systems, for example, in flight control systems or medical monitors where every millisecond counts.
Now let us see how the system actually operates behind the scene. The scheduler constantly monitors the ready queue. It checks if any new process with higher priority has arrived. If such a process appears, the scheduler immediately permits the current one, meaning it pauses the running task, save its state, and give the CPU to make more important tasks. Keep in mind that priority number can differ between systems. In some, a smaller number means higher priority, and in other, it's the opposite. The key takeaway is time-sensitive tasks always get preference to keep the system responsive. Let's understand this with an example where all processes arrive at the same time. Here we have three processes P1, P2 and P3 arriving at same time 0 seconds, but each with different burst times and priorities. Since P2 has the higher priority, priority number 1, it runs first. Then P1, which is priority number 2, and finally P3, which is priority number 3. This demonstrates that even if processes arrives together, the CPU always select the process with the higher priority first. This clear rule-based selection helps maintain predictability and CPU behavior. In this example, the processes don't all arrive at once. They come at different times. At time 0 seconds, P1 start running. At time 1 second, P2 arrive with higher priority. So it stops P1. The CPU switches to P2. At time 2 seconds, P3 arrived but a lower priority. So it waits. The CPU always responds to new arrivals dynamically, switching only if the newcomers has higher priority. This dynamic switching makes primitive scheduling flexible and responsive, but also add complexity. But frequent context switching can also occur.
So let's talk about the advantages and critical challenges. Preemptive priority scheduling has strong advantages but also some challenges. Responsiveness. It ensures high responsiveness for critical processes, perfect for real time application like patient monitoring or air traffic systems. Challenge. Starvation. If high priority tasks keep arriving, low priority ones may never get CPU time. This is called starvation. Solution to this? Aging. To prevent starvation, the system gradually increases the priority of waiting processes over time, like giving older tasks more importance the longer they wait. Next, real world application and implementation. In real world systems, preemptive priority scheduling is the core mechanism of most real time operating system (RTOS). These systems control things like sensors, robots, or industrial equipment where delays can cause errors. The, the implementation relies on two main components: priority queues to manage processes based on their priority level efficiently, context switching to save and restore processes quickly when preemption happens. Also, don't forget the aging mechanism. It ensures fairness by preventing low priority tasks from waiting forever. Summary and key takeaways. To wrap up, let's summarize what we have learned today. Dynamic allocation. The CPU dynamically switches between processes based on priority. Urgent task focus. Ideal for systems where timely execution is critical. Management required. Needs mechanism like aging to prevent starvation. Scheduler foundation. Understanding this concept is key for designing efficient and fair operating system. So, in short, preemptive priority scheduling balances speed, fairness, and control, making it one of the most powerful scheduling methods in modern computing.